I am Sang-Woo Chan from the Department of Computer Science at UC Irvine. And before I get to talk about the in-practice part, the opportunities and challenges part of near storage acceleration, I guess I must talk a little bit about what near storage acceleration is first. Near storage acceleration is the act of putting an accelerator or computation unit on the storage device itself before the data actually has to move over the PCIe or some other communication interlink to be moved to the CPU side. And this accelerator will be charged to do work such as pre-processing, filtering, encryption, decryption, what have you, whatever you might be interested in putting on this platform. And in fact, it's garnered enough interest that there is a couple of industry commercial offerings for the development platform for this kind of use cases. But I guess if we want to talk about near storage acceleration, we need to justify this a little bit. So first we can talk about why near storage acceleration, the near storage portion of near storage acceleration. In the olden days, when storage was much slower than the interlink between the storage and the CPU, everything was good. Storage was slow, the software and the CPU just kind of worked around it. But as storage became faster than the typically allocated, for economic reason, the typically allocated and provisioned intercommunication bandwidth between the storage and the CPU. In fact, if you look at publications from Samsung and these other places which actually build storage, typically the provisioned PCIe bandwidth is something like 2 times slower than the available peak internal bandwidth of the storage device itself. In this situation, if your software was smart enough to make the best use of storage access characteristics, then very quickly the PCIe or some other interconnect, it could be Ethernet, some other interconnect between the storage and the CPU will become the performance bottleneck. One solution to this could be to implement a filtering operation on the near storage acceleration platform before the data has to be moved over PCIe. In this case, everyone will become happy again because the required data rate over the PCIe gets reduced again to acceptable levels. And this isn't just a problem within a single storage device. This diagram is from a little bit while ago, from 2019. But if you look at a large-scale data storage and potentially analytics systems with multiple flash storage devices in them, if you look at the bandwidth, the gap of the bandwidth between the PCIe root complex that is allocated on the CPU itself, for example, if you're looking at a single node server class system, a few years ago, maybe 16 lanes of PCIe Gen 3 capable of consuming up to 16 gigabytes per second. If you had connected 64 SSDs onto it, PCIe SSDs onto it, each doing 2 gigabytes per second, which is not very fast by today's standards, there would already be an 8x performance gap between what the CPU can actually retrieve from the storage system and what the storage system is capable of delivering in terms of bandwidth. And not to forget, there's also the issue of having faster internal bandwidth compared to the PCIe link between the SSD and the coming out of the SSD itself. One solution to this could be to have near storage accelerators on the storage device itself. And this is actually one of the goals that, for example, Samsung is trying to explore. And if we have filters, for example, which can consume all of the internal bandwidth that these internal storage flash chips can give us, then we will absolutely be able to have better bandwidth utilization. So that's the performance aspect of near storage acceleration. So we can move on to the next portion of the question, why near storage acceleration? So the acceleration portion of near storage acceleration. Well, there's 2 parts to this. First of all, and of course, there are other systems and companies and research labs that are focusing on the near storage computation portion without the acceleration. But in my humble opinion, due to the limited power budget of the storage devices itself, for example, with the Samsung SmartSSD, the power budget is only 25 watts. There's not a lot you can do with general purpose processing capabilities within this 25-watt budget, especially since the performance requirements for these near storage accelerators to be effective is quite high. For example, if you have a PCIe Gen 3x4 storage device, which is kind of the norm nowadays, the embedded storage computation unit needs to be able to process 3+ gigabytes per second per device. And this is not something you can readily achieve unless you have really good computation fabrics. So in our research, we are typically looking at using FPGAs, field programmable gate arrays, which are ASIC chips, which can be I mean, I don't have to talk about the FPGA benefits to this crowd. FPGAs are typically known to be at least as capable of GPUs in most applications, while being able to provide a significantly higher power efficiency. There is a slight issue of the fact that it's quite more difficult to program, but maybe we'll have a time to talk about that as well today. So coupling higher bandwidth of faster internal bandwidth, coupling that with the higher processing capabilities within the power budget of an accelerator, we are ourselves and many other research teams out there have demonstrated much faster performance using these near storage accelerators, even compared to much costlier software systems with enough DRAM memory capacity to not have to access storage at all. So these three are, you don't have to pay attention to the details of these charts right now. These three are from some of the papers that we've published within the group for database join queries compared against MongoDB, log template extraction against Splunk, and graph analytics versus various near storage, various storage-based and in-memory graph analytics systems. We have demonstrated that with careful design of the accelerator, we are able to achieve much faster performance compared to costlier software. Again, with much lower power consumption. So this sounds really potentially too good to be true. If we put in a new piece of hardware, low power consumption on the storage device, and we magically get this much significant performance increases, then why aren't everyone else doing it yet? So the catch here is that you probably can already imagine is that there is a really significantly high, as of yet, significantly high complexity of development due to the heterogeneous aspect of near storage accelerators. Say we have a storage device coupled with an accelerator connected to the CPU over PCIe. There's a lot of moving parts that we have to keep in mind when we're developing a efficient near storage accelerator. First of all would be that, of course, the existing software must change because the semantics of storage access change. It no longer is a dumb block level storage device. You have to program it to computation, you have to give it parameters, and the data that gets returned for every page that you send the read request to may not be the same number of bytes that you asked for because of the computation semantics. And of course, due to the accelerator having to function within a strict power budget on the storage device itself, sometimes the CPU or the GPU on the host side may be better for some portions of the application. For example, one of the most prominent issues that we've discovered is that the accelerator memory, the DRAM memory on the near storage accelerator itself is relatively slow. So sometimes you have to work around that. Also, the accelerator itself the near storage accelerator implementation needs to be fast enough to keep up with the storage bandwidth. If the accelerator provides good computational efficiency, for example, in terms of gigaflops, but it is not fast enough to keep the storage device busy at all times, the accelerator now becomes the bottleneck. And if the accelerator becomes the bottleneck, we lose the potential to not have that bottleneck by allocating more powerful accelerators on the CPU side, ones with less, for example, power budget requirements. At the same time, the semantics of the accelerator should not cause I/O amplification. For example, for every page that is read from storage and sent to the accelerator, it should not, the size of the resulting intermediate data or the size of the resulting data in general should not be larger than the input data. Otherwise, we're back to square one. PCIe will become the bottleneck again. And another caveat is that typically we can only support one-way data movement. If we read something from the storage, process it at the accelerator, sent it over to PCIe. If the application requires that the data to be transferred back into the accelerator over PCIe again, that typically incurs too much data movement overhead to be effective. All of these are complicated and important moving parts, and I hope to talk about most of this with the prominent exception of automatically changing the existing software. Because this is still future work for us, And two, I guess this is that's not the focus of my talk as it is planned right now. And due to these kind of restrictions and moving parts and the difficulty of optimizing for this heterogeneous environments, if you look at many of the near storage accelerator publications, convenient targets typically are simple filtering operations, encryption operations, compression operations, things like that, where for example, if there's not a lot of off-chip memory accesses, then we don't have to worry too much about which of the work that we have to allocate to the near storage accelerator as opposed to the host side GPU. So here we hope to at least go a little bit beyond this to go into more complicated and more industry-focused applications as well. And as a result, I guess, of us going through multiple conventionally complicated applications for near storage acceleration, we have come up with a very short checklist we go through every time we explore a new application on which we want to accelerate on the near storage accelerator. The checklist comes in two parts. First, the application or the algorithm implementation has to have no FPGA bottleneck. And the FPGA bottleneck could either come from the requirement of having high parallelism inside the algorithm to make up for the lower clock speed of the FPGA, because FPGAs are typically clocked at, as you are familiar with, either 200, 300 megahertz, as opposed to the gigahertz of clock speeds of typical CPUs and GPUs. Also, because due to the power constraints, the onboard memory capacity and bandwidth are kind of limited, we need to have low memory capacity and bandwidth requirements in the algorithm. The second part of the checklist is that it needs to have no I/O amplification. Is the output of each accelerator application smaller than the input data, or at least can it be compressed and decompressed effectively? This was one of the bigger hurdles when we were dealing with floating point intensive application, but I don't think we will talk about that today. And again, is data movement one way? Once the data is pushed through the near storage accelerator, does it never have to come back to the storage? If we can satisfy both of these checklist items, then we can always keep the storage busy with useful work, and we introduce no new PCI bottleneck, which at the very least would result in the near storage acceleration being useful, not introducing a new hurdle or a performance bottleneck. So the majority of this talk from now on, I hope to go into case studies of how this checklist was applied to some of the more prominent applications that we dealt with, and how they kind of prompted the change in algorithms and accelerators for the applications that we cared about. I have three case studies ready in this talk: unstructured log querying, graph analytics, and convolutional neural network inference. Incidentally, from the abstract for the next talk I saw on the website just now, I have a feeling that we're probably going to be talking about similar things. Beyond this, we actually did a lot of interesting point application explorations on near storage accelerators. We've done database joins, nearest neighbor search, floating point compression, a lot of things. But today I will be focusing on at least these three applications with bigger emphasis on the unstructured log querying application, because this one, first of all, it's the most recent, and second, it was done in collaboration with VMware. So logs. Analyzing logs, unstructured text logs generated by software in conventional computer systems can provide valuable insight. If we do deep analysis into these unstructured logs using log analytics software systems, then either by using tools such as statistical analysis, causal graph analysis, or even neural network based approaches, we can, it is shown that we can obtain very deep and valuable insight in applications, including intrusion detection and crash detections and things like that. But there's a couple of prominent hurdles when dealing with unstructured logs. The first most prominent difficulty is that system logs are typically unstructured text. So here's an example from an HPC, high performance computing log. And because these logs are generated in a human readable, unstructured text format, there is really no predetermined schema to the structure of the logs. For example, important keywords can appear at different offsets within a line, and sometimes they may be completely unstructured. This means this kind of a data structure is not really good for more regular data structures supported by database management systems, for example. And instead of having a predetermined schema, the so-called format string in unstructured logs encodes the type of the event. For example, format string would be the string that you would use in a printf statement to format your parameters into the human readable text form. And this is what is called, for log analytics, this is what is called a template. And for each unstructured log line, the template to which this log line belongs to must be identified for the system to actually extract useful data from each line. Which means if you want to do queries into unstructured log, then it requires parsing unstructured text. And this is a very performance-intensive task. So that's difficulty one, that's hurdle one. So hurdle two is logs are typically large and cold. For example, if you look at enterprise or HPC use cases, I'm sure everyone here is much more familiar with this than I am, can generate terabytes per second, terabytes of logs per day. And most of these logs are very cold, not very high usage rates. Typically what will happen is that as soon as logs are generated, they would be stashed in secondary storage somewhere, potentially compressed in a compressed format, and then only take it out to process it when there is need. This means in order to do effective log analytics, then we do need high storage performance. And just a little bit more of background is a little bit more of background into how to actually parse logs using templates. So looking at the same unstructured log excerpt, each of these lines would actually belong to a single template in a pre-constructed library of format strings for each template. For each template, for the same format string, it will have the same schema, which can be expressed in terms of tokens, existence or non-existence of tokens in which location. And this library of templates will be generated either by a human expert or an algorithm. And one of the useful template extraction methods, algorithms, is a so-called frequency tree templates. And this is what we have focused on for the purpose of this work. Given a unstructured log line, the algorithm for extracting the frequency tree template can concisely extract key tokens, which are colored red and underlined in this example, key tokens to construct the frequency tree. So by parsing this large example log, the algorithm can construct a library of templates in the form of a frequency tree, where the closer to the root of the tree means that these tokens are globally more frequent inside the entire log structure. So in this tree, each leaf represents a template, and which is color-coded according to the example on the top. And to traverse and to determine which line belongs to which template, each token in each line must first be sorted by the global frequency of all of the tokens in the log, and then traverse the tree in that order. Of course, you can imagine that the act of sorting each element, each token in each line would be a pretty computationally expensive operation, especially since it has to be sorted by the global frequency, not just the frequency within each line. And of course, if you're talking about accelerators with potentially lower clock speeds, then traversal of the tree is also a pretty expensive operation because it is not readily parallelizable type of work. So we apply this application, this algorithm as it exists now, to our checklist. Is there no FPGA bottleneck? Does it have high parallelism? No, it does not, because we have to do graph traversal into the frequency tree. Does it have low memory capacity and bandwidth requirements? No, it doesn't, because we have to sort every input by the global order. And the global order array is actually a pretty big, of at least a few hundred megabytes size data structure that needs to be held in off-chip memory. Is there no I/O amplification? Yes, actually, this one is true, because if we are able to do template match-based filtering, then the output of the data will be at least the same or smaller than the input data, because we would be filtering rows. So naturally, the focus of trying to implement this particular application on near storage accelerators would be trying to improve the no FPGA bottleneck portion of the checklist. So to give a spoiler first, I'm going to describe the internal design of our efficient log query accelerator. And the task of this accelerator is that we're going to match and filter each log line based on the query. And the accelerator, unlike the base application, the base algorithm that I described just now, it supports a so-called disjunctive normal form of tokens, in that it example of a query that it supports looks a little bit like this in the form of disjunctive normal forms. Each term here in the set equation is a token, so for example, kernel or error or something like that, and each term can be negated. And all of these terms are organized into one or more intersection sets connected by intersections, and all of these intersection sets are joined by unions. So basically the disjunctive normal form of tokens. An example query could look something like this. And the number of tokens that are supported by the hardware for each set and the size of sets are defined by how the hardware is implemented, and we'll get into that in a few slides. So we built this accelerator. The question is, how does this accelerator, which looks very different from the tree traversal workload that I've just talked about, how does this support template-based filtering, template-based querying? And this is how these two things are reconciled. So given a frequency template tree, each path from the root to each of the leaves can be encoded as an intersection set. For example, this is the colored path is for template 3 from the previous example, going over RAS, kernel, and then fatal. And the path to get from the leaf root to the leaf can be encoded using an intersection set of whether each token should exist or not in the line. For example, RAS should exist, fatal should not exist, kernel should exist, info should not exist, and then fatal should exist. It could be this can be encoded in this set format. You might notice that there are two fatals in here. One is negated, one is not negated. The solution to this is we get rid of the negated part if this happens. There is a slightly complicated proof to why this works. It's actually in the paper, but I don't think I have time to go into it right now. So once we have this intersection set for each path, then we can encode this intersection set into a hash table, which would be the input to the near storage accelerator. We actually use a cuckoo hashing for space efficiency, but I guess this is not critical to the design of the accelerator right now. And you may notice that in the hash table, there are multiple sets of, there's a set of flags, valids, flag and the negative flag, meaning is this line in the hash something that we should parse? And is this line supposed to exist or supposed to not exist in each line? And we implemented an efficient hardware hash table for parsing tokens in this manner. So given a cuckoo hash implemented inside FPGA block RAM, each of the tokens were assigned 16 bytes in size. And of course, because each token can actually be larger than 16 bytes, we actually have an overflow table also implemented inside FPGA block RAM. We have, in our prototype implementation, we have 8 sets of flag pairs for valid and negative flags, representing 8 potential queries. So how many intersection sets can we have per union set? And we also have the parameter of having, in our prototype, we have 256 rows in the hash table which represent how many tokens can we have per intersection set. We can guess how many based on the fact that cuckoo hashes statistically do fit as long as we have lower than 50% load. With this structure, because we have a hash table and because we also have an overflow table with the same width of 16 bytes, we can make one table reference per cycle, meaning for the string input, unlike having to use, say, a regex accelerator to compare the input 1 byte at a time, we can ingest 16 bytes invariably every single cycle. So the internal architecture of the filtering engine is maybe less important for our purposes right now. Inside each pipeline of the filtering engine, we have a decompressed unit. We store the data in a compressed format, and we came up with an algorithm for an FPGA optimized string compression algorithm, but we won't have time to go into this right now. So after the decompressor, we also have the hash filter that we talked about in the previous slide. Each of these units working at 16 bytes per cycle at 200 megahertz, giving us about 3.2 gigabytes per second per pipeline. And this is already enough to saturate the PCIe bandwidth of many PCIe Gen by 4 storage devices. But an interesting observation was that if we take the decompressed raw text stream and then break it down into tokens, then each of these tokens are not necessarily always 16 bytes. They're not always making the best use of the data path. From our benchmarking, typically on at least HPC system logs, we seem to have about 50% effective bandwidth over the 16-byte data path. So the solution to this was simply to have 2 hash filters. And then we fit as many of these pipelines as we can fit on our target platform. In our prototype system, we were able to fit 4 pipelines, which would give us a theoretical peak bandwidth of 12.8 gigabytes per second. So the prototype platform which we implemented our system on was actually the MIT Blue DBM prototyping platform, which I was a big part of when developing. Our initial goal was to deploy this onto the Samsung SmartSSD, but at the time when we were doing this project, we didn't have the toolchain set up correctly yet. So at this time, we went with the system that we knew how to use. And we modeled the performance of the Blue DBM-based platform onto the Samsung SmartSSD performance characteristics. We have 2 VC707 FPGAs, each with 2 filter pipelines, because the capacity of the SmartSSD FPGA, the ultra-scale Kintex, is about roughly twice the size of the VC707. The internal storage of the storage devices, the flash chips themselves, added up to about 4.8 gigabytes per second compared to the 3.1 gigabytes per second bandwidth over PCIe, which is a realistic 1.5x difference between the internal and the external bandwidths. And with 4 pipelines, we were able to get something like a 74% FPGA utilization, which is a pretty snug fit. It would be difficult to fit much larger designs on this FPGA. And the whole design was synthesized at 200 megahertz. We evaluated the system using real-world HPC log datasets. Some of these were larger than others, typically in the range of 30-ish gigabytes in raw text size. And we extracted the templates because we are not application experts. We algorithmically extracted templates using the frequency tree-based template extraction algorithm. And to do a fair comparison for cost and other things, we also over-provisioned the software system with better storage bandwidth for the benefit of the doubt for the storage system. They were provided 7 gigabytes per second, significantly higher storage bandwidth than the FPGA system. And if you just look at the performance throughput of the filtering engine itself, the cuckoo hash-based filtering engine, the end-to-end performance that we see for template-based filtering is significantly higher than the peak PCIe bandwidth, which is 3.1 gigabytes per second. So this is the benefit of having near storage processing with faster internal bandwidth, coupled with the compression, which we didn't talk about here. The 4x decompressor, the 4 times decompressor maximum throughput, as I mentioned before, should be 12.8 gigabytes per second, but unfortunately we didn't reach that exact number due to issues such as skew in token length causing head of line blocking. Comparing against software performance, first we compared the raw string parsing performance against software. We compared against MonetDB, which we assume would give us a pretty well-optimized software implementation. And we tested just the text string parsing operation by disabling the index. We used a randomly composed set of template queries because we are able to support up to 8 parallel sets. So we tested composed sets of 1 sets, 2 sets, and 8 sets. And if you look at the performance of MonetDB, as we can expect, the performance in terms of effective throughput becomes slower as we add more terms into the query, as we club more sets of template queries together. Compared to that, because our FPGA system can invariably consume 16 bytes per second, regardless of, as long as it doesn't exceed the number of sets that are supported by the hardware, we will see invariably high performance. And this is interestingly the same for much smaller logs as well. This VGL2 log is smaller than a gigabyte. Even after the entire log is cached in memory and became hot in memory for the software system, the same kind of performance difference is already there, which tells us the bottleneck is indeed storage computation performance. So how performance effective is Mithrilog in the light of this? So because there isn't exactly we weren't able to find an exactly hardware implementation for log analytics, template-based log analytics, we compared against existing implementations of regex-based log analytics system Hawk and a low overhead LZRW1 compression algorithm. So if we compare the number of LUTs necessary for each gigabyte per second of throughput, we can see that our FPGA optimized algorithm for doing text parsing gives us orders of magnitude better performance efficiency in terms of performance per LUTs compared to the comparison system. And because even our design fits pretty snugly into the target system with 70-something% utilization, then if we can tell that with conventional systems and conventional designs for regex-based parsing, we cannot have enough throughput to actually keep the storage device busy. But of course, the caveat is that regex-based systems are a little bit more flexible, so there is that caveat. Comparing the end-to-end query performance against software, we compare against Splunk with index and the usual optimization, the same randomly composed queries. For all of these queries, so this chart is plotting the elapsed time of Splunk on the Mithrilog on the x-axis, which is the name of our system, Splunk software on the y-axis. So everything above this line would be where our hardware implementation is faster. And this, and with more complex queries, combination of say 8 queries, then we can see that our deterministically high throughput gives us a really high performance compared to the software implementation. And this pattern pretty much maintains for all of the logs that we've tested, which gives us a lot of confidence. And lastly, if we could compare the power consumption evaluation, if we compare our FPGA near storage accelerator on the left compared to the software implementation with Splunk, unfortunately, because BlueDBM is a less optimized implementation of a storage device, the power consumption of the storage device itself is significantly higher compared to the off-the-shelf server system. And of course, there's also the added overhead, power consumption overhead of the FPGA. But thankfully, because it does reduce the processing overhead inside software, the overall power consumption of our FPGA system, of our near storage accelerator system, is actually lower than the software system. And we should note that we are lowering the power consumption. We are even lowering the power consumption while improving the performance by potentially multiple orders of magnitude. Okay, so that was our unstructured log querying example. I actually have much shorter versions of these two other applications, but in the interest of time, I think I should probably skip over graph analytics for now. And if there's interest, maybe I can get back to it later. So I'm going to skip over this. The basic idea is that if we do graph analytics, they're very random access intensive on each vertex and across vertex traversals, meaning we're going to have random access into memory. So the most prominent hurdle in our checklist here is that if we want to do graph analytics as a near storage acceleration offload, then random access into a large vertex array would kill the performance because of the low performance of the embedded memory. So we created a sorting-based approach to sequentialize the access into the memory, massage the algorithm pretty much. And compared to existing software systems, we actually get significantly better performance, even while reducing the power consumption by an order of magnitude or more. If there is interest, I can come back to this later. And I guess I'm going to spend just a little bit more time talking about our ongoing work on convolutional neural net inference in the near storage accelerator. And at this point, I'm sure I don't have to really preach to the choir about the importance or the structure of neural networks. But I'm just going to reiterate that typical convolutional neural networks are composed of multiple things, but also including convolution layers on the left, which scan a small, in this example, there's things like 5 by 5 convolution filters by scanning this small filter over the input data, and fully connected layers, which are basically matrix to vector multiplications. The question here is, what do we offload? If we want to accelerate neural network inference on near storage accelerators, what do we offload to near storage? So this is where our checklist comes back. Is there a high parallelism? Yes. Systolic arrays and matrix multiplication inherently has very high parallelism. That's good. Does it have low memory capacity and bandwidth requirements? It actually does not, because for fully connected layers, which are pretty much large matrix vector multiplication, with the meager memory bandwidth that these near storage accelerators have, we have noticed that typically the fully connected layer inference becomes bound by memory bandwidth really, really quickly. Is there no I/O amplification? Yes. If you only send classified labels, then the data rate over I/O would be decreased significantly. The observation here is that the fully connected layer is almost entirely memory bound, especially with the low memory bandwidth on the near storage accelerators, meaning given the same chip resources, we do suffer order of magnitude slower performance than convolution layers. So what would happen if we only offload the convolution layers into our accelerator? Do we have no FPGA bottleneck? There is really high parallelism, yes, because of systolic arrays. Is there no low memory bandwidth? Yes, because for convolution layers, there's very small number of weights relative to the fully connected layer requiring pretty much no off-chip memory accesses in our experience. Is there no I/O amplification? Typically, this is true because the feature map connection between the last layer of the convolution and the first layer of fully connected layers are typically much, much smaller than the input. So this could be only offloading the convolutions may be a more useful use of near storage acceleration from the point of view of gigaflops per accelerator. Unfortunately, one caveat here is yes, there is high parallelism in terms of systolic arrays, but it doesn't actually mean, if you try to offload all of the convolution layers, it doesn't actually mean that the FPGA does not become a bottleneck, just because the raw amount of gigaflops that's required to do all the convolution layers is a little bit too high for the kind of accelerators that are on the storage device if we want to maintain line rate performance. So how do we get around this problem is our ongoing work. So here's an example architecture for a systolic array for convolution acceleration. We have row buffers on the left to get the 3 rows necessary for the 3x3 convolution filter. We have multiply accumulator units, an array of them, 3x3, according to the size of the filters. And also we have the array adders, which adds all of the output from the multiply accumulator unit and turns it into a single output. And based on this architecture, Our current ongoing work is to go further, to accelerate only the first layer. And this has benefits beyond just lowering the number of gigaflops that we need to do. Because in our previous processing element architecture, if we can reduce the size of the processing element on the chip, then we can have a larger processing element array, resulting in the increase in the amount of gigaflops you can do, of course. Multiple existing and well-explored methods for doing this include reducing the size of the weights and activations from float 32 to float 16, float 16, and smaller values. In our work right now, we're mostly focusing on floating point. We're not focusing on int 8s, for example, because we have seen some accuracy requirements that do require floating point. And our observation here is that a significant chip resource portion of float operations is the process of normalization in floating point operations. After you do floating point multiplication or additions, maybe I should have an animation here, the mantissa portion, if it has many leading zeros in the MSB, then the mantissa has to be shifted upwards until the most significant bit is non-zero, as you see on the bottom example, the 1, 2, 3 exponent and 1, 0, 1, 1s. And this, if we are to use off-the-shelf floating point operators, then this normalization process with variable with shifters must be done after each float operation. And we've noticed that this is a pretty significant chip resource overhead. And how does this play into accelerating only the first layer? Because the input to the first layer is just 8-bit integer pixels, meaning if we don't restrict ourselves to perfectly normalized formats in the floating point, we can fix the exponent at compile time because we know that all of these information are only 8-bit values. And if you're only processing one layers, we can hard code the weights to each of these filter onto the FPGA itself, meaning because the number of weights are smaller, meaning the input and weight exponents are known at compile time. And the results, the exponent results of each MAC operation can also be determined at compile time. At least a very narrow range of MAC results can be determined at compile time. Meaning, we keep going, meaning is the array adders for adding all the MAC operation results can align each of its inputs with fixed width shifters, because the amount of shifting each array adder needs to do is already determined at compile time. We do not need expensive variable width shifters anymore. We can use fixed width shifters. And normalization process is only required once at the very end of array adders, which really, in our experience, reduces the chip resource overhead of convolution accelerators. So here's the checklist again for our only first layer accelerators. Is there no FPGA bottleneck? This is different across models. We are still discovering, but yes, we have high parallelism because of systolic arrays. We have low memory capacity and bandwidth requirements because we're actually encoding weights, hard coding weights into the circuit itself. The problem here that we're trying to work on right now is there no I/O amplification? And this is a definitive maybe, because the feature map size of the first layer output as opposed to the last layer convolution layer output may actually be larger than the input. Of course, this still results in more useful near storage acceleration in terms of gigaflops, but we have to now solve this problem of I/O amplification. And that's where our current project is right now. Typical convolution neural networks do have max pooling layers after the first convolution layer to reduce the feature map size. And offloading the convolution as well as max pooling layers can reduce the data transfer size. For example, for AlexNet, if we use float 16 and we offload the convolution layer and the first max pooling layer, there is no size increase after the max pooling process. But unfortunately, some models such as ResNet do have size increases even after the first max pooling layer. To address this right now, we're exploring compression, both in lossy floating point compressors and lossless fixed point compression algorithms as well. I'm sorry that I can't give concrete numbers for these kind of things, just to be talking about, oh, this is better or this is worse. But hopefully we plan to have very concrete results for this soon, and maybe I can come back to talk about these results in a bit. So that has been a very quick zoom over the three case studies, three important case studies, at least we think, of the applications that we work with. And I guess the conclusion that we have from all of our exploration is that if we want to have effective near storage acceleration, it must consider, first of all, heterogeneous system design. Take into account memory performance, take into account the balance of performance between the near storage accelerator and the PCIe and the host side accelerators. And in order to achieve this, the algorithm that we implement and the architecture that we implement it on may also need to be manually optimized for hardware characteristics. And this can feel a little bit daunting, especially for people who, if you want to sell this to people who are not familiar with FPGA acceleration. And this portion is leads to our future work. If you take a step back a little bit and you look at the process of model discovery in science, typically, I guess people start with a very simple model of understanding nature. For example, on the leftmost side, these are symbols for fire, water, earth, and wind, I think. And after a while, people discover there are such things as elements, and they build the complicated table of periodic elements. After which, based on our understanding of the complex system, we were able to come up with a more simpler abstraction of atoms and electrons. And I guess looking at all of these case studies, I am still here in the complex discovery phase of model discovery. I hope to, and I think we're getting close. Based on our observation with these complicated point application explorations, we hope to move to glean out and extract the simple model, which can benefit hopefully all of the near storage acceleration that people want to do in the future. So a little bit closer look at what we want to do would include things like languages and models for efficient accelerator development. We could be looking at domain-specific languages for expressing streaming systolic arrays. Hopefully, the programming model for the thing that we want to build will enforce the checklist, which I was talking about. Hopefully, it can be something like P4, what P4 does for networks. And we are also trying to explore consistent software interfaces to support accelerators. For example, how do we transfer complex parameters and inputs like hash tables into the near storage accelerators? How do we send I/O requests with embedded type information, for example? And of course, we also need to explore more complex applications with less storage-friendly patterns to make sure that the things that we're going to build in the future that can be applied to pretty much everything that people care about. Applications we're looking at right now may include things like graph neural networks, which will provide us a pretty significant challenge.